So last time we did the version of greens that's known as the circulation version. So this is what you know so far. Whoops, I don't know what's going on there. Sorry. Huh, interesting. Doesn't let me write. There we go. So you know this green. So if you have a line integral and it's a closed curve and it's a simply connected region, go ahead and convert it to a double integral where the integrand is dn dx minus dm dy. And the relevance of it is if you had your bathtub or your jacuzzi and you put a little paddle wheel in there with little vertical paddles, it would spin or not spin. And the direction it would spin would be given by the value of the integral that you do here. So if you get a positive result, the little paddle wheel is spinning in the counterclockwise direction. And the absolute value of the result is going to give you the idea of how the speed of the paddle wheel turning. And you can get 0, and that just means the paddle wheel is just sitting there and it's not turning. So there's another version of greens that computes flux, and we mentioned this a little bit. And so if your unit tangent vector, which you use for the other vector here, because this is really the same as f dotted with the unit tangent vector ds. If you look at this where you've got the unitized version of the velocity vector, your n, you want the dot product of t and n to be equal to 0. So if you've got this is your t and this is your n, if you notice, you're going to have like x prime dotted with y prime. I'm kind of ignoring the denominator since they're the same, plus negative x prime times y prime, and that of course will be 0. So it's going to work out. So that's the flux version here. And so then when you use greens with this version of it, you've got f dotted with n. So you're projecting your force vector onto the unit normal vector because you want to figure out the amount of water or whatever it is flowing out of your region, outward. And now you take the dot product of your vector field with your unit normal vector, and then you get mn, and then what about this ds, which is your arc length element. Don't forget, little ds is your arc length element. So it's like, oh, well, what happens to that guy? Or what is that guy? And I hope you remember it's going to be the magnitude of r prime dt. Well, what happens if you after you do your dot product and everybody has this denominator of r prime, that is going to cancel essentially. So all you'll get left is m y prime, which is dy dt. And so you end up with m dy, and then minus n dx. Notice this line integral looks different from the first version of greens, which is m dx plus n dy. Very different. And it turns out that this, after doing all the dot product out, ends up being the partial of m with respect to x plus n dy when you convert to greens. So when you apply greens. So there you have it. That is the alternate version of greens. So this is the alt version of greens. So you definitely want to write this down somewhere. If you're making a sacred formula sheet somewhere, then it would be good for you to put this down somewhere. And on your quiz this weekend, a lot of the problems I'm going to ask you to do, and Briggs is because it's from the text, do both versions of greens in one problem. So you have to do the circulation version and then the flux version. That's right here. Okay, so know how to do it. And if your outward flux ends up being a positive number, that means more of the fluid is going out than going back in, and so on. So if you look at this little example where your force field is a cute little vector field xy, here's m and here's n, dm dx is 1 and dm dy is also 1. So when you do this together, you get 1 plus 1, which is 2. So that's a positive number. So that means you're going to get more fluid flowing out than flowing back in. And we're going to look at the 3D version of flux next week when we do the divergence theorem. So I'm planting a seed for later. Great. So this is a typical problem right here that you'll see on the quiz this weekend, as well as a midterm and a final. So know how to do it. It's not that hard because all you do is apply your greens. So they want us to find both the circulation and the flux. So we're going to use both forms of greens. Here's the vector field. The region R is going to be an easy region. It's just the unit circle, which is a circle of radius 1, centered at the origin. So it's oriented counterclockwise. So anytime you see a circle, what do you think? Don't you think polar? I hope you do. Eventually, you may have to convert to polar. So let's do the circulation version first. And that's the original greens that you learned. And so I'm just going to repeat it just for review's sake. It has the look of your line integral looks like mdx plus ndy. And green says, oh, turn that into a double integral where you have the partial of n with respect to x minus the partial of m with respect to y. And so we're going to do that. And so here's n, dn dx looks like it's 1 minus dm dy. That looks like -1. Okay. But that's going to be 2. Oh. And remember I taught you last week, if you're lucky enough to get a constant, you can pull it out in front. And then what? What does this double integral represent? Isn't that representing area? Anytime you have a double integral with a 1 as its integrand, that's an area. So we don't even have to convert to polar. I mean, we could. I mean, if they said, okay, go do it the hard way, you're like, okay, R lies between 0 and 1. Theta is going all the way around 0 to 2 pi, la, 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 you know, and then R, d theta, etc. But why do that if you can do the shorthand? So this is really the same as area of the unit circle. And so we know pi r squared, that's just going to be pi, and don't forget to multiply by 2. So final answer for the circulation is 2 pi. That's a positive number, which means if this force field represents the velocity of some water moving around, we would be able to put that little paddle wheel in there and get it to spin in the counterclockwise direction. Cool. Now let's compute the flux. So now we want to know if we submerged this little unit circle into that bathtub or the jacuzzi, would there be more fluid flowing out, or would there be more fluid flowing in than out? Or maybe the amount of fluid flowing in cancels out the same amount of fluid flowing in and you would get 0. So the flux version of greens looks like this, mdy minus ndx, and that says convert to a double integral, only the integrand is a little different because you're still going to take some partials, but you're going to take dm dx this time and add it to dn dy. Okay, so let's make sure we do this correctly. Dm dx, let's go back up here. Here's m. When you take the partial of x minus y with respect to m, you're going to get a 1. Plus, now let's do dn dy. Since n is simply x, when we take the partial of x with respect to y, ooh, what do we get?
You get 1.
Well, when you take the partial of x with respect to y, not x, but y.
Oh, dn dy. My bad. I thought we were talking about m.
Yeah, we did get that already. Dm dx was indeed a 1. You're right.
That's going to be 0.
0. Dn dy. Good, good, good. Oh man, that's just a 1. Cool. So, you know, we just get a 1, which is just there. Okay. But wait a minute. When we have a double integral and there is only a 1 in the integrand, doesn't this represent area of the region? Yeah. And that's once again pi r squared, but that's just going to be pi. So since the flux is positive, that means there's going to be more fluid flowing out of from the boundary of this region than flowing in. Okay, cool. Good to know. Okay, any questions so far regarding circulation and flux? You see that this problem actually has two parts to it. You got to do both. So usually those are worth a lot of points. So when I give one of these on a quiz or on an exam, don't just do one of them and then move on and forget that they want both. Okay, do both so you get all your points. Circulation, flux. Will they all be this easy? No, this one was kind of easy because we never really had to evaluate the double integral because we got kind of lucky. But some of them may not be so lucky. Some of them you might actually have to set up a double integral and, you know, put your little man in there and put your limits and all that good stuff. Yeah, so don't forget how to do that. That's super duper important. So what I want to look at now is regions with holes, and I'm having trouble locating it in my notes here, but I think we skipped it a little bit. Let's go back. Okay, so we had you do some stuff last time, so that was fun. So let's look at doing regions with holes. Okay, what about regions with holes? Well, in the Green's theorem, we didn't talk about regions with holes because we were making one of the conditions for Green's to be valid was for simply connected regions which don't have holes. So it's like, wait a minute, holes aren't simply connected. You're not allowed to do that. But it turns out you can. So I lied. What do you mean? Well, let's just look at a region that's got a hole in it. Let's say there's a hole right there. Okay. Man, how do you do that? So the idea is you grab a knife. You grab a knife and you cut a slit into your region right there. This is called a slit. Okay, you cut. Well, then what? Well, then what you're going to do is you're going to here's your starting point, and you're going to go around the outer boundary of your region, and we'll call that C1, in the counterclockwise direction. Okay, but then, so your overall curve is going to be a combination of curves, C1. Then once you hit the original starting point, you're going to then move inward towards your hole along the slit. So we'll call that portion of the journey C2. So that little curve going along the slit is C2. Now, once we hit the hole, you have to go around the boundary of the hole, because part of Green's is you have to cover all the boundaries. So if it's simply connected, it only has one boundary, the outer boundary. But if you got a hole, you got to worry about going around the boundary of the hole. Now, here's the part that's weird. In the Green's theorem, we said you go around counterclockwise. But when I was mentioning that, and you may have forgotten this, I mentioned, hey, when you drive around your outer boundary, you need to be able to look over your left shoulder and see the land. So it turns out once you hit the hole, you have to go around the hole clockwise, not counterclockwise. Well, how come? We'll call that little curve C3. How come you have to go around the hole clockwise? Well, think of, again, driving. If you were driving around that hole boundary in the clockwise and you look over your left shoulder, you still see your land mass here. Okay, this is your land mass, and you need to see it over your left shoulder. So that's why C3 goes around clockwise. Weird, huh? And then you have to always end up where you started. So the last part of your journey is you got to go right back to where you started. So after you go around the hole there in the clockwise direction, then you go back along the slit, but in the opposite direction, and you end up right back at your starting point. Because remember, you got to, the starting and end points have to match, closed curve. So you have to, do you have to do all four line integrals? No, of course not. It turns out that the curve 2 and the curve 4 cancel. Why? Does anybody want to gander a guess?
The, uh, is it because they're perpendicular to each other or orthogonal?
Well, they're just going in opposite directions. So from one thing that you should have learned so far in line integrals, and if you haven't yet, maybe now is the time for you to finally glean this very important piece of information. When you do a line integral going in one direction and you get an answer, if you go in the opposite direction, you'll get the same answer, but opposite in sign. Okay? Have you gleaned that piece of information yet, or maybe not? So C2, whatever, when you do a line integral over C2, since C4 is in the exact opposite direction, those line integral results would cancel because they would be opposite in sign. Okay, so you really only have to worry about C1 and C3. All right, so that's it. That's all I'm going to say. So I'm just going to say C2 cancels C4. Let's do a cute little line integral that involves a boundary with holes, okay? And this is similar to what I put on your quiz as well as your exam, so it's worth looking at. Example 2, very cute. So let's say you have a region that has an ellipse, but it's inside of an ellipse, but outside of a circle. So the region looks like, if we graphed all of this, and if you got this in standard form by dividing both sides of the equation by 36, so you can figure out this standard ellipse centered at the origin has x intercepts plus or minus 3, and y intercepts plus or minus 2. So there's our ellipse. Okay, and then, but it's outside of this circle, and this circle is a unit circle centered at the origin like this. So the region has a big old hole in it. Oh, but now based on what I just told you, holes are okay. We're okay to do this using greens based on what I told you. Now we're not actually gonna do any line integrals though. We're gonna take this line integral and convert it to a double integral over this region R. It's got a big old hole in it. Yeah, sure. It's totally okay. We can do it. What would the curves be? Even though they're not showing it. The curves are understood to be, well, let's say the outer curve would be going around the outer boundary in the counterclockwise direction, and then you would make that slit again here, and then you go along the slit, but that cancels, and then you go around the hole. We'll call that C3, or you could call it C2 or whatever, in the clockwise direction, all right? And then you go back to where you started from along your slit. But the slits end up canceling. So yeah, you don't care about that. All right, so now when we set this up, let's go ahead and get dn dx. So n is this guy here. So when we take the partial of n with respect to x, I think it's going to be 2 plus 2x minus dm dy. Here's m, and when you take the partial of 2xy with respect to y, you will get 2x. Oh, that's very convenient. So you notice what happens? These 2x's cancel. Oh, that's lovely. And then what? Well, you get one of those lucky ones again, where you just have a constant for your dn dx minus dm dy. Pull it out. And so you guessed it, this is going to represent area. So what's the area? It's going to be the area of the outer shape here, which is the area of the ellipse, minus you cut out the area of that inner shape, which is the circle. Now you just use your knowledge of areas of ellipses and circles. So you know pi AB minus pi r squared. So here we'll get the A is the distance from the center to the horizontal boundary there, 3, and the B is 2, and this is a unit circle, so the radius is just 1. Oh, that's convenient. And this looks like, what, 6 pi minus pi in parentheses, 2 times 5 pi. I get 10 pi. Yay, and we're done. And there you have it, regions with holes. Questions? Pretty easy? As long as you know your area of ellipse. I want to say something about more than one hole, because I don't want you to get into a habit of thinking, oh, you are only allowed one hole. What if I did have 2 holes? Just say real quick here. I'm not going to do an example with 2 holes, but I want to show you this just for your future math career, because if you end up taking complex analysis, you may see something like this. Yeah. So you would go all the way to the outer boundary, and we'll call that C1. You'd grab a knife. Yeah, you got to have a knife. And you would make a slit here, and you'd also make another slit here to connect the 2 holes together. Okay. Then what? This is where it gets a little weird. You'd go along the first slit. So your overall C is going to be the union of a bunch of curves. And now be careful here. We're not going to go around the entire first hole here. We're going to go around in the clockwise direction, the underside of that hole. And then once we hit the slit, we're going to go along the slit, the second slit. We'll call that curve C4. And then once we hit this other hole, we'll go all the way around the other hole in the clockwise direction, because you want to be able to drive and look over your left shoulder and see land here. Then once we get back to the slit, we drive back over that slit, which I guess we'll call that C6, but C6 would cancel C4 based on what I just told you. And then once we get to this first hole, then we drive the other half of its boundary. We'll call that C7, union C7. And then we'll drive back along the original slit and back to home right there. We'll call that C8. So we have a lot of curves just to get around all the borders of this region that's got a couple holes in it, but it don't matter. And you can extend this to as many holes as you need. Yeah, and that's it for holes. Now, to wrap up greens, I did an overall summary flow chart for you that I made up. I didn't find this in any book. I came up with it, and it's my gift to you. Oh, here's another meme. Spent a half hour parameterizing a curve from noxious line integral. Realized the vector field was conservative. Okay, here's a big summary of line integrals. So somebody gives you a line integral. Boom. Here. Enjoy. So what do you do with it? Well, first you have to identify if the line integral is type 1, 2, or 3. We talked about this. If it's type 1, and which means it's a scalar line integral, no vector fields involved. You have some density function, and you integrate the density function essentially, and then you have an arc length element. And the type 1 represents the mass of a wire, basically. So whether the curve is closed or not closed, it doesn't matter. It has to be a parameterized curve. And if it isn't already, then you may have to go parameterize it to get the vector valued function. And you're not allowed to have time go backwards on these, because you don't want to get any negative answers. Make sure when you do your line integral, you don't forget the arc length element, because that's a common student error to forget this. And then your final answer should be positive, because this represents the mass of a wire. Although I have seen some textbook exercises end up with different results than that, which is kind of unfortunate, but whatever. They put together something where the density ends up having it go negative. All right, so what if your line integral isn't type 1? What if it's type 2 or type 3? Those are the vector line integrals. FDR is type 2. And if somebody already did the dot product for you, you end up with this differential form. So what if you get that type? Well, one of two things. You have to check if you want to make it easier for yourself. Check if is the vector field conservative or not, because that'll make all the difference on your strategy. So if it is a conservative vector field, then you go down this path, and now you decide, is the curve closed or not? If the curve is closed, the answer is going to be 0. Remember that from the equivalent conditions? So you don't really have much work to do. You're just like, hey, I'm done. 0 is the answer. No work needed. If it's not a closed curve, well, okay, then you have a little bit of work to do, but you can make it easier for yourself if you go on and use the fundamental theorem of line integrals. I mean, if you do it by brute force, you're going to have to parameterize and do it the hard way. So you don't have to parameterize the curve, but you do have to find the potential function. And once you get your answer, it may be positive, negative, or 0, because it's representing work done on the object as it moves around the vector field. So work can be positive, negative, or 0. Now, on the other path, what if the vector field was not a conservative vector field? What if that were the case? You again want to ask that question, closed curve or not a closed curve? If it is a closed curve, cool beans, man, you can use greens. You don't have to evaluate the line integral. You don't have to parameterize, blah, blah, blah. You just do it. And then your answer may be positive, negative, or 0. On the other hand, if it's not a closed curve, you're not allowed to use greens. And since it's not conservative, you can't use the fundamental theorem of line integrals. So you're going to have to, unfortunately, do a lot of work. You got to do your line integral. You got to make sure it's parameterized if it isn't already. And, you know, and the good news is I let you have your t time go backwards if you need it. So that's cool. So there's your summary. And I hope that you appreciate that little flow chart I made for you to kind of summarize everything we've done so far. So that concludes the Green's theorem. We're going to do 17.5 divergence and curl now. This is a fun section. It's fun. You're just going to learn a couple concepts about vector fields. How do you get the curl and how do you get the divergence of it? And it's not that hard. It's easy peasy. You'll love it. Why do we need these? The answer to that will be pretty much next week. But do know how to find divergence and curl. So some preparation work first. This differential operator, which looks like an upside down triangle, and you've seen it before when we use the notation for gradients. You can think of it as being a vector. Really? Ooh, that's weird. Yeah, think of it as being a hollow vector that just has ddx, ddy, and ddz in it. Well, how does that work? Well, when you find the gradient, you're using this differential operator on the scalar function f, and you get df dx, df dy, and df dz. This is a vector field. And remember, it is a conservative vector field, just because all gradient fields are automatically a conservative vector field. Fine. So now let's move on. What's curl? Well, you're going to use this differential operator, which you can think of as a hollow vector, because when somebody says, hey, I need you to go find the curl of the vector field, which is denoted curl F, which is found by taking the cross product of this hollow vector and your vector field, and it ends up being a vector. If your curl is 0, we say your vector field is irrotational. Now, what I want you to do is I prefer that you not do this and use this definition to get your curl. I want to see this when you do a quiz or exam. Well, how come? Because you're in your future, you're not going to remember all this, but you can very easily derive the curl if you remember the determinant method. And that's why I want you to do this for your future. And this is all physics stuff. So how do you get the curl of a vector field using this 3x3 determinant method? There's no difference, Nathaniel. It's the same thing, but I want you to get your answer using the 3x3 determinant method. Ha ha! That's all. So what you do is you put ijk across the top, like we always do when we do a cross product. But the second row, you're going to put the components of this hollow vector. Remember, the hollow vector is this guy here. You'll put ddx, ddy, ddz. And then along the bottom row, you'll put m, n, and p. So you guys know the deal. You're going to have a 2x2 vector here, or 2x2 determinant rather. Let me just do the intermediate step. What does this 2x2 determinant look like? Well, if you block out the row and column that I hat lives in, the 2x2 vector, or the 2x2 determinant rather, sorry, would look like that. So when you do the major diagonal product, so you're multiplying those together, you're saying take the partial of p with respect to y. That's that first guy there. Minus, and then you do these guys here, and that means take the partial of n with respect to z. And then multiply that by I hat. Minus, and then this 2x2 determinant would be found by blocking out the row and column that j hat lives in, and you have these guys. You take ddx of p minus dm dz. And then this guy would look like ddx, ddy, mn, and you'd go, okay, dn dx minus dm dy. So that's how you get your curl. Now your curl is a vector. So don't forget, the curl is a vector. And you can put it in component form if you want to. I usually do, just to let you know that's kind of how I roll. But, you know, there's always more than one way to denote a vector. So let's do an example of finding a curl. And I'm going to use the 3x3 determinant method to do it. So here's a vector field, fine. And they want to have us answer some questions. And we will in a minute. So I'm going to take the cross product of this differential operator with the vector field. So here's my 3x3 determinant method. Put I hat, j hat, k hat along the top row. Second row, ddx, ddy, ddz. Bottom row, the components of my vector field. Okay, here we go. 2x2 I hat minus 2x2 j hat plus 2x2 k hat. Fill in the blanks. Okay, so the 2x2 here is going to be ddy, ddz, x squared plus z squared 2yz. This guy is going to have ddx, ddz, 2xy, 2yz. And over here we'll have ddx, ddy. I know this is kind of a pain in the butt, but that's how we roll. Do it the long way. Yeah, no worries, Jake. Glad you're here. Welcome. Okay. So now what? Okay, do all this stuff. So I'm going to write all this out. So what you have here is take the partial with respect to y of 2yz. We'll do that in a minute. Minus ddz of x squared plus z squared. And that whole mess will multiply with I hat. Minus, and then we'll do this other guy here. Ddx of 2yz minus ddz of 2xy times j hat. That's a j. Plus, here we're going to go ddx of x squared plus z squared minus the ddy of 2xy k hat. Okay, and then now we're just going to do all these partials. I mean, you know, except my PDF annotate's not being very nice to me. So when you take the partial of 2yz with respect to y, I get 2z. Minus, and when I differentiate x squared plus z squared with respect to z, I get 2z. Oh, heck, that's going to be 0. Does that always happen? No, but we got kind of lucky there. This guy, the partial of 2yz with respect to x, that's 0, minus the partial of 2xy with respect to z. Hey, that's 0 again. Oh my gosh. Ddx of x squared plus z squared. Oops, and that's a minus. Sorry, what am I doing here? minus, and the derivative of x squared, wait a minute, d dy, what am I doing here? Did I write that wrong? No, that's d dy of 2xy, right? That's also going to be 2x. Oh my goodness, that is going to add up to 0 also. So what do we get? We get a vector that's 0, 0, 0. Okay, and that is irrotational because they told us if you get your curl to be the 0 vector, it's irrotational. Now, is it conservative? Well, here's the part I want you to look at. Do you guys remember that to test if a 3D vector field is conservative, you have to check if 3 things are true simultaneously? I did that in a previous lecture. And one of them you already knew. You have to check if dn dx is the same as dm dy. If those are equal, you're well on your way. But you also need to check if dp dx is the same as dm dz, and you have to check if dp dy is the same as dn dz. That's right. So what am I saying? If you get the 0 vector as your curl, it's conservative. Yeah, it's a conservative vector field. So another way to check to see if a 3-dimensional vector field is conservative, just figure out if his curl is the 0 vector. Voila! Pretty cool, huh? You should be very excited. I know I am. So that brings me to this next theorem. Test for a conservative vector field in space. If you have a 3D vector field, it's conservative if and only if the curl of F is equal to the 0 vector. And if and only if means you can read this in both directions. So I can also read it, well, if the curl of F is the 0 vector, the vector field is conservative. That's cool. So it's conservative if and only if, and I'm just going to write all these equations down again. You've seen them. dp dy has to be the same as dn dz, dp dx has to be the same as dm dz, and dn dx has to be the same as dm dy. Those all have to be equivalent at the same time. Okay. Are you guys ready? I think I'm going to put you in, you know what, I lied. I said I wasn't going to put you in buddies, but I think we may have time today. So how about you and a buddy do this guy? You're going to go get the curl. That's right. So you're going to get that vector field and find the curl. It's not that hard. Just give it a shot. You know, Kimberly, I know you're on the roll there, but you may or may not want to participate. I don't know if you're in your car. She's driving across the country. Oh my goodness, that's just nuts. Put your mic on so you can talk to your buddy and work on doing some curl. That's right. We're not trying to find out if your hair is curly or anything. We're just doing curl. Well, why do they call it curl? We'll get to that in a little bit. There's a reason why it's curled. So have some fun with curl. Enjoy. What am I doing? Close all rooms. I don't know what I'm doing. Sorry. I'm a mess. Sorry. My bad. My bad. Let me get rid of these breakout rooms. Keep going back and forth. Ah, what am I doing? Okay, welcome back to the main session. I'm hoping that you got a little bit of a feel for finding curl. It does take a little bit of work, right? A little bit. You got to get some partials. So that's why I like you to do it the slow way. Okay, so I'm going to share screen again. Quick question, is this a conservative vector field? Yes or no?
No.
No. You should not have gotten the zero vector for this curl, not like that other one I did. So you probably got some weird thing. But here's the other question: is curl a so the answer to this one was no. No for that guy. Is curl a vector field or a scalar function? What do you think? Anybody?
A vector field?
Yeah. Yeah. Curl is a vector field. So if you did it the hard way here and you took the differential operator cross product with your vector field, oops, you're going to have ijk across the top. What am I doing here? I hat, j hat, k hat. Your hollow differential operator in the middle row, and then your components from your vector field along the bottom row. Oop, I got a plus C here. Boy, am I running out of room. Let me get rid of this bar here so I have some more room. Y cubed Z squared. Okay, so you got this. And then I like to do this on the fly. So I'm going to have ddy of y cubed Z squared. So that's going to give me 3y squared Z squared minus, this right here, the partial of 2x squared y plus z. I think that's just going to be a 1. And that's going to multiply with I hat. And then minus, don't forget this is a minus here, something times j hat. So let's do this. You're going to have ddx of y cubed z squared. Well, there's no x's in there, so 0. Minus ddz of xy squared z to the 4th. Well, that looks like it's going to be 4xy squared z cubed. So that's kind of ugly, but all right. And then you're done with the j hat component, and then you'll go plus something times k hat. So you're going to have the ddx of 2x squared y plus z, and I think that's going to be 4xy. Minus partial with respect to y of xy squared z to the 4th. That looks like it's going to be 2xy z to the 4th. And you're pretty much done, although you may want to clean this up a little bit. One of the ways I like to clean up is this minus and this minus will end up being a plus. And I like component form. That's just personal preference. My lab math may ask you for, either one. So be ready. Just follow directions on what they want you to put in there. And this is a vector field because it's a vector. It's not a scalar function. That's for sure. You've got you got ijk involved, so it's a vector. Okay, so we're done with that, and I hope you got something, and here's my meme. Is there such a thing as curl of a two-dimensional vector field? This seems like a trick question. Because curl involves cross product, and you remember from cross product 2-3 months ago, you need a three-dimensional vectors to cross product with. So technically, no. Although they do ask for the curl of a 2D vector field in your homework. So it's like, well, what? So what you can do is if you embed your 2D vector field into 3D, what happens? So if you had, let's say you had a vector field that was really only 2 dimensions. Okay, so you only have the x and y. coordinate axes. And so you've got M, N here. That's 2D. How do you take a cross product of a 2D vector? Can't. So the idea is you still want to be able to talk about curl of a 2D vector field is you say, well, I'm gonna embed it into the world of 3D. So then your last component, since you are staying in the XY plane, your Z is zeroed out. So when you do the cross product of this whole thing, you're going to end up with, if you did, you know, this curl, oh boy, hang on a quick second. Power problems. When you do this curl 3D whole thing here, you're going to end up with, you know, 0 essentially, because you got a 0 there. 0 minus dn dz. You'll end up with dm dz here because it's minus minus, and then you'll get dn dx minus dm dy. But this is 0 and this is 0. Well, how come? Because n only has x's and y's in it. So if you take the partial of n or m with respect to z, you're going to get 0. So what happens is your curl of your 2D vector field ends up looking like 0, 0, dn dx minus dm dy. Well, if you did take the dot product of this curl, this right here is the curl of f, with k hat, so you'd get, you know, 0, 0, dn dx minus dm dy, dot product with 0, 0, 1, that's k hat, you would just get dn dx minus dm dy. That's it. And a lot of times books will say, well, that's considered the curl of the 2D vector field. Okay, if you want to go there. But while we're at this point of talking about curl, I want to say something about greens and curl. So you guys remember that the form of greens, let's just do the circulation form. mdx plus ndy is the same as the double integral of dn dx minus dm dy. That's greens, which we just finished, but you got to know it. This is considered, you know, the curl of f, although I just showed you they like to write it as curl of f dot product with k hat dA. So a version of greens you may see in some calculus books as well as some vector calculus textbooks is this. And I don't want you to freak out and go, well, that's not greens, because it is. So I just want you to know that's another way of putting greens, but bringing curl into the conversation. Oh, interesting. So let's stop talking about curl for now and move on to divergence. So that's the second half of this section, because we're talking about curl and divergence. What is divergence of a vector field? It's really easy. It's much easier to get than curl. Good news. So 2D divergence, div for short, it's the dot product of the differential operator, that's that hollow vector, with your vector field. So if I did it in slow motion, it would look like ddx, comma, ddy, dot product, mn. So ddx times m gives you dm dx, and then ddy times n gives you dn dy. That's it. And for 3D, it's the sum dm dx plus dn dy plus dp dz. If your divergence is 0, your force field is said to be divergence free. It doesn't mean it's conservative though. So here's that dot product with the differential operator I just showed you. So I'm going to do an easy divergence problem. So we're going to find the divergence for this vector field and then evaluate the divergence at a point. All right. So here we go. Really easy. You're just going to go divergence of f is dm dx plus dn dy plus dp dz. Just get it, okay? You don't have to even do the dot product. Just get it. So what is the derivative of m? Here's m right here. with respect to x. Add that to dn dy. In this case, it's going to be 0. And then dp dz, oh, that's also 0. You don't always get that lucky, but so we just get this. Then if we evaluate the divergence of f at the point 2, 1, -1, you're just going to substitute, you know. And I get -12. Okay. So what is divergence? You can think of it as a sort of weird derivative where if vector fields were representing velocities of moving particles like wind or water, it gives you the rate of particle fluid flow per unit time at a point. So it's like how much particles are moving at that point at any given time. And here they'd be moving in the backwards direction. So if you've got a divergence-free velocity field, then it's incompressible. If you have a vector field that's divergence-free in the world of electricity and magnetism, it's called solenoidal. And this is actually a big physics thing, so know this. So I'm going to give a theorem in a moment, but before I do, I want to give you a cool mnemonic. Okay, mnemonic. Do you notice how curl involved a cross product? And the word cross product has a letter C as the initial letter, and curl has a letter C as the initial. Whereas divergence of F involves a dot product. And the word dot product starts with the letter D as in dog, and the word divergence starts with the letter D as in dog. Do you get it?
Yeah.
Curl, cross product, divergence, dot product. Yeah. Okay. So do the concepts of divergence and curl have anything to do with each other? Good question. They have some relation. And there's two biggie theorems that I want you to know. So biggie theorem number 1, so this is biggie number 1, says that if you got a vector field and m, n, and p have continuous second partial derivatives, then here's what's true. If you take the divergence of a curl, you'll get 0. Yeah. So here's the proof. First, let's do what's inside parentheses. So, you know, when you take the curl of a vector field after doing all the cross product, you get a vector field. And so the components are dp dy minus dn dz, and then the opposite of dp dx minus dm dz, oops, parentheses, comma, I got too many commas going here. And then the last component is dn dx minus dm dy. Okay, fine. So if you take the divergence of this curl, which also can be denoted del cross F. You got a lot of these upside down triangles running around here. It's crazy looking, isn't it? There's a dot product right there. So what are you doing? You're taking ddx of this first component, like this, because that's what the divergence says to do, plus the dy of this second component here, which this has a negative in front of it due to the fact that it was a 3×3 determinant, plus ddz of the last component. Okay, this is a short proof. We're almost done. You'll love this proof. So now I'm going to distribute like so. And so when I get the first term, I know this is a second partial, people. It's d squared p over dx dy. And if I did this using the subscript notation that we can also use when we do partials, it would look like pyx. That's what that would be. But I'll stick to this differential notation. And then the second, after I distribute, I'll get d squared n over dx dz. And over here, I'm going to distribute the dy, and there's a negative there, so it's really opposite of d squared p over dy squared, like so. That should be dy d. That's dp dx. Sorry, I had some bad notation there. This should be dp dx. Sorry, dy dx. And then a minus minus turns into a plus, so I'll have d squared m over dy dz. All right. And then the last distributing over here in the corner, I'm going to have d squared n over dz dx minus d squared m over dz dy. Boy, this is one hot mess. Okay, now here is the cool beans part of it. Do you guys remember that mixed partials are equal? Do you remember like fyx is the same as fxy? Do you remember that?
Yes.
Because that's going to come into play, baby. And we're going to cancel everything out. What do you mean? Yeah, this one, pyx, and then we have minus p xy. Oh, cancel. Yeah, nice. Anything else? Well, this is a minus d squared n dx dz, and we have plus d squared n dz dx. Cancel, adds to 0. And one more, we're not done. We got more coming from where that's coming. Yeah, d squared m over dy dz minus d squared m dz dy. Big fat 0, and yay, I'm done with the proof. That's the biggie. Divergence of curl gives me 0. Now, there's a second biggie theorem relating divergence and curl, although it's not really divergence and curl. It's, to be honest, it's relating curl with a gradient, because this is not divergence. Well, you've got that differential operator, I know, but phi is a scalar function. So this is really another way to denote this would be grad phi, gradient of phi. Okay. So know that. I'm just looking for a book I thought I had here. Don't have it. Darn it. Okay. So if you take the curl of a gradient, you will end up with the, not 0, but the 0 vector. I'm not going to prove this. I'll let you prove it. One time I put as extra credit on a final exam, prove the second biggie theorem. And one student did pretty well. And it's going to involve mixed partials or equal. So work it out on your own for fun. I'm not saying I'm not going to put it on there, but I could. Okay. So if you notice this guy's t-shirt, he's got Green's second identity, divergence of the curl, which we just did with the first biggie theorem, divergence of the gradient, that's the second biggie theorem. Oh, I didn't do curl of the curl, but you can take curl of a curl. Yeah. So one thing I want you to get before we do the last page and wrap this lecture up is 2 key points. When you take the curl of a vector, you get a vector field. Okay? Your answer should be a vector. It's a vector field. When you take divergence of a vector field, the result is not a vector field. It's a scalar function. It's not a vector field. And if you don't believe me, if you look at that one problem I did up here, example 3, when I found the divergence of this vector field, see, I got this 3x squared y squared z. There's no ijk's involved here. There's no vector notation, nothing like that, because it's not a vector. It's not a vector field. It's what we call a scalar function. Scalar function. Nice. Okay. So knowing that, let's look at my grand finale here. So when you take vector calculus, if you plan on it, which we don't offer here at Southwestern, but it would be next in the calculus sequence if you were at, say, UCSD, you would go on and take it. And I've had students who take my Calc 3 and then they transfer to UCSD and then they take vector calculus. And they usually do pretty well because half that class we've already done here. You know, when we did Green's theorem and double and triple integrals and stuff like that. So some of the vector calculus stuff, you'll see it again because you'll hit it. You haven't hit all of it. You'll see. Now, let's look at div, that's divergence, grad, that's short for gradient, curl, and all that jazz. So let f be a scalar function and then uppercase f be a vector field. State whether the following are meaningful or not. And if they are meaningful, say if it's going to be a scalar function or a vector field. Okay, let's do these one by one. Here we go. Curl of f, meaningful or not? Well, I just taught you curl of f. Of course it's meaningful. and it's a vector. Okay, gradient of f, meaningful or not?
Yes.
Yeah, of course. You know, we did this like 2 months ago. Gradient of f, no problem. You know, it is a vector because it's a vector that has the partials in it. So it's definitely meaningful and, you know, no worries. Okay, divergence of f, which looks like the dot product of that differential operator with your vector field. Of course it's meaningful and you'll get a scalar function. Okay, now we're going to get weird. The curl of grad f, which you could rewrite using a lot of upside down triangles. Remember, curl is a cross product. So take the cross product of the upside down triangle with the gradient of f. Is that meaningful or is that just nuts? Nothing. I'll give you a hint.
It's zero.
It's a zero vector. Yeah. And it is meaningful. It's Biggie theorem number 2. Biggie theorem number 2. Yeah, it's a vector. Specifically, it's the zero vector, not just any vector. It's zero vector. Now, what about gradient of a vector field? Can you take the gradient of a vector field? No, you cannot. That is meaningless garbage. You can only take the gradient of a scalar function and have it be meaningful. So be careful. That's yucky. Okay, what about letter F? Can you take the gradient of a divergence of a vector field? So if I use little triangles here, I got the gradient. There's the gradient of this dot product. Letter F. And I claim it's meaningful. It's like totally okay. Really? Yeah. You're just taking the gradient of this scalar function, which has a special look to it. It's d, oops, I'm writing too quick. What can I say? And this is a scalar function. And you're allowed to take gradients of scalar functions. You'll get, you know, a vector that contains the partials of that scalar function. And so you will get a vector. And it's totally meaningful. How about the divergence of gradient? So you remember divergence it involves a dot product here. And this is a vector field. And you are totally allowed to take the divergence of a vector field because gradient is a vector field. So you're totally allowed to do this. This is legal. So, you know, they're just saying take the divergence of this vector field here. And you will get a scalar function because that's what divergence gives you. So it's totally meaningful. We're good to go. Letter H, can you take the gradient of the divergence of a scalar function? Well, first of all, you can't take the divergence of a scalar function. That's meaningless yuck. So that right there tells me can't do it. You can only take the divergence of a vector field, not divergence of a scalar. Can't do it. So this is not good. Not good. Okay, how about curl of a curl? That guy's t-shirt. Look at this guy's t-shirt. He's doing a curl of a curl. So it must be legit. Yeah, it is legit. It's totally legit. Curl over curl is legit. Totally okay. And you got a lot of cross products happening there. First you take the cross product to get your curl, and then you take the curl of a curl, and you will get a vector. And it's meaningful. It's good. How about divergence of divergence? No, you cannot do that because This, the first divergence here, is a scalar function. And remember, this is a dot product here. And you can only take a dot product between a vector and a vector. So this scalar function isn't even a vector. So this is meaningless, not okay, can't do it, makes no sense. Okay. Two more. Can you take the gradient of f, which I hope you know is a vector, and take its cross product with divergence of f? Keeping in my mind that divergence of f is a scalar function. Can you take the cross product of a vector with a scalar? You guys should know the answer to that. Yes or no?
For divergence.
Can you take a cross product between a vector and a scalar?
No.
No,
No.
of course not. No way. Meaningless. You can only take a cross product of a vector with a vector, folks. Yeah? Yeah, not good. How about the divergence of the curl of a gradient? And I didn't put the little triangle things here, but I'd be going divergence of curl with gradient like this. Can you do that? And the answer is yeah. And you'll get 0 because this is Biggie theorem number 1 in action. They actually, in the Biggie theorem, you are actually taking the divergence of curl. All right, so there you have it. All the possibilities. Now, if you thought this page was a waste of your time, if I were you, I'd hold on to your course reader because you will thank me later when you get to a vector calculus class. They may ask you some of these exact same questions because I pulled these from a vector calculus book. Okay, fun times. All right, some tattoos for you to think about.
Cheating?
This person is physics. These are some physics formulas actually. But I just thought this was hilarious that this person had all that written right there, you know, arm tattoos. Good times, good times. Okay. All right, folks. So that is pretty much it for us today.